Hello and welcome to another video. And today we have the second MSI Tomahawk. If you didn't catch the first video, this is a letter of review that has sent in multiple motherboards, and he wanted to get two MSI B550s fixed. And in the last one we fixed the first one, which is still right here with me. This one is fully working now. And now we are going to be fixing the second one. And I don't know what is wrong with this board, but I would also do physical inspection first because I can already see some scratch marks on this. And the other one also had physical damage. So let's have a look at this board now under the microscope first in order to see if this also has physical damage. So the area where I saw scratches was at the left side of the board, close to the SIO. You can see where these screw holes are. But this damage seems to be only at the screw hole. Let's have a look now closer to the SIO. We have some scratches here. But I don't think there are missing components here. Like that one, for example, is not a missing component, I'm pretty sure. Right there. I don't think that there's a missing component. There's just scratch marks on some pads, just like here as well. So yeah, after seeing those scratches, I was like, yeah, we will have to take a look at that area first. But there seems to be a lot of these. Cannot really tell how something like that happens. Like why there's so many different scratches. And the area where we had damage the last time was here in this area where we had missing components, and here. But not this time. This time this looks fine. Let's have a look at around the CPU socket, which very often has damage. Nothing here this time. And now at the top of the socket. Also looks fine. Let's go to the PWM controller up here. That looks like corrosion right there. I don't think there was a component ever there. Nothing damaged here. Looks to be fine, just that corrosion is a little bit weird that we have that there. Like if you can see just here. But I don't think there was ever a component fitted here that we're missing. Let me quickly see on the other board that I have still lying around here. No, there's no component there. Okay. So another thing that I saw is that a corner of this is partially delaminated, as you can see right there. But that corner doesn't really matter, I'm pretty sure, because there's only ground there. And if we look at the back side of the board, you can also see that delamination at the corner. But nothing special. That capacitor looks very weirdly discolored compared to every... no. Seems to be fine. MSI loves to put components on the backside of their boards. And I had many different MSI boards that were suffering from no V-core because of missing components on the backside. Because there's very often like enabling stuff and similar things running on the backside of the board, especially here in the middle of the backside of the board. But so far it seems to be fine. Like we saw so many scratches at the front of the board, but it looks to be a lot cleaner on the backside. Yep, so far so good. Nothing special. With all the scratches that I saw, I really expected it to be some knocked off components somewhere. But so far, this looks all fine, and this is basically all of the backside. Well, there might still be something on the front that is like hiding from me somewhere, because knocked off components just can be basically everywhere and often are very hard to spot. But I really thought when I saw these scratches that there's going to be something at those scratches where I saw them. But it seemed to have not. Oh, there's a little bit of damage. You can see at that capacitor right there. But that shouldn't matter. Don't think that that capacitor will be shorted because of that. Yeah, nothing here. But yeah, this looks like there has been corrosion here. We will definitely have to check for some resistances before we put power into this, just to be sure. Because it really seems like there was actual water damage, especially under the heatsinks that it was able to spot some. So let's go into the overview and take our first measurements then. So let's see now. We're going to take a ground point. And let's see now. 3.3 volts. Has high resistance. 5 volt VSB. Has high resistance. 5 volts. No, this is 12 volts. This is 5 volts. All has high resistance. P is on. Has high resistance. That is all good. Let's check the VPP phase. 1.8 volts. All looks good. This phase right here. No, don't know what that is. All of those look fine. Let's see for the SIO area. And checking random capacitors around the SIO. Seems to have high resistance. That looks good. Let's check the 12 volt phase. High resistance. This should be 0. Yeah, and now 12 volts into the phase. High resistance. Okay, so all of the resistances seem fine for now. At least the few that I've checked. And we will definitely be able then to put a processor now in here and see the behavior that we have. So on the last board, we saw a weird power up behavior where we had too much passive power consumption of like 300 milliamps, but the board was still working in that condition. And now on this one, we're going to see how this one will behave and what kind of power consumption we can see on this one. So got a 2200G in here. Let's get a power button into here and also a speaker. We have one stick of RAM in here. Let's get the power attached. And let's see now. And this one looks fine. We now have 110 milliamps. That is what I would expect. Let's see if we have a reaction to the power button. And we do not have a reaction to the power button. Yeah, no reaction to the power button. Let's see if we have voltage on the power button then. Let's start like we always start when we have no voltage. Yeah, and no reaction to the power button. We do have 3.3 volts. Okay, what we can do, we can push the PS on, short that to ground to see if the board is not wanting to start up because it senses something that is bad, or if the board is just not where the PS on is just not reaching the actual adapter. If it now turns on when we do this and we get postcodes, then it's actually just some physical damage or something like that. And if it doesn't turn on, or if it just gets stuck from a CPU LED, there's an actual signal somewhere missing. So let me short that and see. Yeah, 300 milliamps. With 300 milliamps, there's something not starting up. So something isn't, some major voltage isn't there. I would guess that like 1.8 volts or something like that isn't starting then. Let's see. 1.8 volts is present. Let's see then here. But this is okay. Let's check the 3VSB then. 3VSB is also present. Let's see, can I probe the 5 volt dual somewhere here? No, cannot probe the 5 volt dual. It's under the heatsink. But we will probably have to check around the SIO then, because something seems weird here. See, 3.3 volts also there. Okay, so it's not reaching. So we now will have to check if the power button press is actually reaching the SIO. So we will have to take a good look at the SIO probably once again. And I want to also take the heatsink off of the PCH in order to see if there's any damage there. And I want to probe the 5-volt dual that is also hidden under there. So let's see if the 2.5 volts is actually running. Got the heatsink off of here. But it does not seem to be. Let's see, the 5-volt dual is here. But shouldn't there be 2.5 volts here somewhere? Because I'm pretty sure we are missing the 2.5 volts that should be here in standby. Let's go under the microscope again. So this is the area I'm talking about. The 5-volt dual comes in here via this choke. And from this one and from this one, we should be getting the 2.5 volts going into the PCH. There's definitely some dirt under here, but I'm not sure if this is like water damaged or not. The question is, why there should be 5 volts coming in here. 3.3. Is this the output then? Yeah, this might be the output for it then. But I feel like there should be 2.5 volts here somewhere already. Interesting. Okay, this is so far a dead end for me. I'm not too sure where the 2.5 volts... Let me check a board view where the 2.5 volts should be. So I've taken a look. And this should be right here, 2.5 volts. And I see nothing right there. And this is the enable pin of it, and the enable is low. So I feel like this will be our problem. I'm pretty sure this is in standby, so that we should have 2.5 volts there, but we don't have. Let me show you that in a board view. So look at this. This is the controller. And we have 3 VSB as an input right here. And we have two 2P5V feedback there. And we have an enable for 1 P05 enable right there. And this is not present. And we do not have 2.5 volts as an output right here. So the question is, where is this enable signal coming from? Let's see. This is to ground. This resistor goes to sys V in. And this takes 5-volt dual. Yeah. So through this choke into this resistor, we should have 5 volts. And this should now then be for the enable there. Because this is the drain. So the only thing is if this is active low because of this this double MOSFET. So we should have 5 volts dual there, and if we have no voltage here, then it's because of this double end channel MOSFET there, where the gate is enabled and drain is being put to source, and source 2 is ground, which connects then drain 2, and this is gate 2. So if this gate is enabled, we probably have no voltage here. So let's see if that is actually true. So let's see here. Oh, you couldn't see all the voltages all the time, huh? I'm an idiot. I'm very sorry. Now you can only see the voltages. I hope I pronounce them every time. And now you actually will be able to see them. So let's see now. We want 5 volts right here. is, oh no, it's not on here. So now we have passive power consumption again. And let's see now. We want 5 volts dual right here. Right there. Yeah, 5 volts dual. And on this side, we don't have it. So I would guess that we have probably voltage here. Yeah, we have voltage there, so this is being pulled low then. And we get voltage from here, which is the 5 VSB. Yeah. So this gate here is connecting these two together, which this is ground and this is the 5 volts. And this is also the enable signal for this one right here. So I'm not too sure why this is present, why this is working like it is. This is kind of weird to me. I will see in a schematic if I can understand what is happening here actually. So let's see now. We have, this is our transistor right here. We have 5 VSB that is coming in here, and it is enabling gate 2, which is pulling this to ground always. Sleep state 3 and sleep state 5. This I'm not getting this too much. So the ATX 5 VSB is always present, basically always present, which means this gate is always enabled, which connects D2 and S2, which means this right here, the 5 volt dual for the VIN and the enable is getting pulled low all the time. How is this supposed to work? Only if ATX 5 VSB is being pulled low somehow. VSB enable. If we take the, oh yeah, that's how it works, I think. So if we have sleep state 3 present right here, it's going to pull G1 low, G1 high, which then connects S1 with the VSB enable. Yeah, that's how it works. Yep. Because if then the ATX 5 VSB is present, it's going to be pulled low through this transistor at the bottom right here. And then this gate isn't being powered anymore, which gives us the 5 volt dual as an enabled signal on U38, which then gives out the 2.5 volts. So the missing thing that we have is sleep state 3 currently. So we will have to see why we don't have this. Sleep state 5 isn't a factor here because this 0 ohm resistor here right here is not there. So we will have to check on R3272 if this is present and if we have sleep state S3 or not, because we want this gate to be enabled. So let's check for this resistor right here in the board view. So let's see now. The resistor that we have is this one right here, and we want to see voltage on it, but there probably isn't voltage on it. So let's see where this sleep state 3 is coming from. It should be coming from the processor, if I'm not mistaken. Oh, this uses the double AND gate solution. Yeah, I know what that is. This is just a gate, so let's go through all of these signals. And this is probably also just an enable signal, also going into the SIO, probably also just an enable signal here. This is where it origins from. This is the output of a double AND gate where we have to look at. This is probably also just an enable. This is the enable for this gate that we saw. Then this goes onto the 100K that we saw there where it origins from. This is not fitted. This is just on a gate and this is just on a gate. Yeah. So we will have to take a look at this thing right here. If we have what is happening right here also. Because this is a dual AND gate that takes 2 inputs. And if those are true, then it will pull its output to its VCC pin. So if this and this is high, it will pull this pin to this pin. And that's what we want and need. So let's have a look then. So let's see right here. Right there we want voltage. The board doesn't hold on. Now we have passive power consumption. And we can see this has the 5 volts. Yep, and we want to see 3.3 volts right there. So our S3 seems to be low. Yep. No S3. Okay, let's then have a look at the double AND gate right here. So this is the output that we want to be high. So we want an output here, and we do not have that. Let's check both inputs. So let's check this right there, and this is low, and let's check this right there, and this is high. So we're missing this input right there. So what we can do, let's see if we reseat the CPU and maybe plug a different one in even. This might give us already the signal. So different CPU in here, and I try to make sure that it is properly plugged in, and still no S3. Yep, and still no reaction to the power button then. Yep. So we're missing the S3 signal, and it should be coming from the CPU, and it should be the right one, I'm pretty sure. And that is pretty surely just going to be connected to the CPU itself. So let's check that in the board view. So in the board view, we see that this is now low, and this, we have this enable signal, but we do not have APU SLPS3. This is only connected here to ground, probably through 100K, and here to the socket. So the only other things that I know then is that there's like a 1.8 volt signal that needs to get into the CPU somewhere here. Let's see for the 1.8 volts. This is the 1.8, and there's like a few resistors where the 1.8 volts is coming in and then is supposed to be going into the CPU. And like this one, for example, for the RTC line, yeah, something like that. And only that, as far as I know, is basically what you have that could be going into the CPU and could be related to then as having S3 state. For example, here, RSM RST CPU 1.8 volts. Here, for example, you can check this. So let's have a good look at the resistors again and at the back side. So we want to see voltage right there, 1.8 volts, yeah, and there. Is there no voltage on RSM RST? There's really no voltage on RSM RST. That is weird. Is it connected to ground, RSM RST? 21 ohms. Is this like a half shorted SIO again? I had something like that before, where the 1.8 didn't get into the RSM RST properly because of an active short in the SIO. Okay, so we now have power consumption, and when we have power consumption, we see 21 ohms on RSM RST right here. Right there, that is RSM RST. And now I'm turning off the power supply, and now I would guess that we don't have a short anymore, like not 20 ohms anymore. Yeah, now we have high resistance. This seems very similar to what I've seen before. Yep, now it's really high resistance. And only when you have the power going into the SIO, you will have this power consumption. Okay, the last time how I did this is I changed this resistor to a lower value so that more current can pass. What we can do to test my theory, we can inject 1.8 volts into the RSM RST ourselves in order to see if we then get actual S3 or behavior of the power button. So let's do that then. Let's go into the overview. Let's see what the power consumption says if I connect now via my tweezers onto the RSM RST. Only 50 milliamps of power consumption, and we have a reaction to the power button. Do we get further than a CPU LED? 1.5 amps of power consumption and stuck at that. Okay. Let's see if with the different processor it will behave differently. So let's try this again. 1.5 amps of power consumption, but it's not moving anywhere. We don't have a proper startup sequence. So this definitely got us further. because I'm pretty sure now that we also have like the that we do now have the S3 state, but I don't think it's working properly yet. I want to try something else. If we supply S3 completely by ourselves, does this have the same reaction? No, it does not have the same reaction. Okay. So, let's change out that resistor for a lower value, so we don't have to inject the voltage ourselves. The last time I think it was something around a 22k ohm resistor, and I just changed it with like a 1.5k ohm or something. Let's see in the board view this time. So, this time again it's a 22k ohm, so I did remember correctly. Let's change it with a low ohm resistor and see how the board then behaves. So let's change out that resistor that we have there. For that we're going to be starting with some leaded solder on both of the sides of the resistor. So the resistor is out, and let's get a new resistor here. So there's our new resistor now. This is just 100 ohms, I think. Where did it go? There it is. This is just 100 ohms. This won't be a problem because we saw the power draw is really not that high. So it should be fine. So, and I always tend to hot air it into place just to be sure that we have a proper good connection with some flux on there. Getting a good 450 degrees here. So not nice that it's on the backside, but it should be fine. Should be just the same connection as on the front. So let's see that it's properly connected. We should see 100 ohms now. Connected from 2 points. From this point to that point we should see 100 ohms. There we have it. Let's now see how this board now behaves. So let's see now. I would expect higher power consumption, just a little bit higher. We have 1.4 volts, and let's now see if we now get the voltages that we were missing before. So let's first see for the output of the AND gate. We still not have sleep state 3. Interesting. But we do have the 250 ohms. 250 millivolts. This is probably not enough yet. The resistor, I'm probably just going to bridge that. There's still no reaction to the power button. Yeah, we're probably just going to bridge that instead of using a resistor there. So let's get rid of this resistor again. And let's see if I can bridge this just with a good amount of solder. Right there. Now we have a solder bridge there, and the solder bridge is very good connected. So let's now get into the overview once more. So let's see, more power consumption. Yeah, 300 milliamps. And reaction to the power button, but we are still stuck at a CPU LED. Okay, I want to see if we have all of our memory voltages, because something is still ain't right, and I want to see if we actually have sleep state 3 now, or if that is still missing. So let's now see if we now get all of the voltages, and we can see we have all of the DDR voltages, so that isn't a problem here. Let's check if we have the S3 signal now present. And S3 is now present, so that isn't the problem anymore. Let's see, VCore is also present. VPP here should be present. Why can I not probe VPP? 0.5. Okay, this seems weird. We might have to want to probe that again. 105 volts. Now we see 2.5 volts. 1.8 volts. 0.9 volts. All of the voltages seem to be present, so yeah, I'm not really seeing anything that could be a problem now anymore. CPU is definitely getting very warm. So currently it just seems like that our BIOS isn't being accessed. The question now is if we have a good BIOS on here or not. And if the CPU is being recognized or not. Because currently it seems to be in a state where it wants to start, but something is still not there. So let's have a quick look at around the BIOS chip. But I'm pretty sure we had a look and there was everything fine here. This soldered? I don't think someone soldered here. So I think I can use this TPM header right here to flash the BIOS chip, or to at least read out its content. I will be looking into a board view, and I might want to do that just to be sure that the BIOS that is on here has an actual functioning BIOS on. And yeah, let me do that. So currently I have read out the chip, memory read in 33 seconds it says. And it appears to be a whole bunch of nothing. There's some weird spacers here, but there's no data here. There's no BIOS on here. How's this supposed to work? So someone has messed with that. So let me get a proper BIOS onto here. So an actual BIOS, if you open up a BIOS file, let's go for B457C91. If you go for an actual BIOS file, it should look something like this. There's content here. Let's see if this chip is if we are able to actually program this chip. Very often you get errors with, when I see a blank chip, I assume that the chip is actually faulty and we just cannot read or write to it anymore. And it will now be trying to erase. It now will be trying to write only zeros to the chip. And after that, we are actually going to be programming it. And it cannot see when it's writing to the memory if it works or not. And what it does after that, it's doing a verify step. So it's going to be reading after it wrote the chip. And then it's going to be comparing the contents that it wrote to those that it read out at the end. So the verification step at the end is going to be in the important one where we can actually see if this BIOS chip is still good or not. And currently we are at the step of verification. So I'm actually looking forward to this and that this could actually work. Because very often the verification fails early. And then you can already know that the chip is broken. But in this case, it seems to be fine. So yeah, it verified without a problem. We can do that also, just reading out the content of the chip now. And if we now read out the content, nothing should change. All of this should still be there. And then I can just solder the chip back on. I decided to take it off because my programmer didn't want to see the chip via the SPI header, or the TPM header, how it was called there. So in this case, I'm just going to, I just went ahead and desoldered it, put it onto an adapter. And yeah, so let's see now. We should see content now. And we do see content. So I'm positive that the chip is now working and we now have an actual BIOS. And let's see if that is now the fix to our problem. So I gotta say, I'm fairly confident that this might work now, because the BIOS was actually had nothing on it. So let's see. We want to see more than 1.5 amps of power consumption. Yes, 2.4 amps. That's what we want to see. And yeah, CPU LED turned off. I have the post screen should be on here. 3 amps. That is very good. Show me 4 amps. And there's a post screen. Very, very nice. So we had 2 faults here. So we did not only have the fault for the 1.8 volts, for the RSM RST that wasn't present, but we also had a fault with the BIOS. Okay, so I don't know what happened, but someone has tinkered with the BIOS and it was just empty. Because the chip isn't faulty, the chip was able to be written to without a problem. There's a BIOS flashback function on this board, and someone has maybe messed with that. But yeah, so we are going to be trying to get this board into Windows now. For that, I want to put the heatsink on again. The fault with the RSM RST. I just happened to had exactly that fault like quite some time ago. I think even it was one of my videos where I showed that, where I had exactly the same problem, where the 1.8 volts went normally through a 22k ohm resistor into the SIO, and as soon as you had voltage on the SIO, you got an active short. Like I was able to show you, as soon as you had passive power consumption, or like the necessary voltage for the SIO to work, it had a partial short, an active partial short on that RSM RST line and pulled it low to ground. But it's a very, very low current short, because it's not an actual short, it's 21 ohms. It's just lower resistance. But that is enough through a 22k ohm resistor to not have that line working anymore. And with that, the signal, the 1.8 volt signal, isn't reaching anymore, and it thinks it is low. And all what we did is, first we injected 1.8 volts into there, and we saw only 50 milliamps of power consumption, which is nothing, especially for that 1.8 volt line. That 1.8 volt line can easily deliver more. So we are actively pumping more power into that lower resistance, but it works. And I've had that happen before. And I exactly remembered the 22k ohms that were there before. And I just had to change that out. Even with 100 ohms, it wasn't low enough. Only with basically bridging it, it was low enough in order for the 1.8 volts to get there. And yeah, I just, that is just experience that I had that exact same fault before. Like, that is very lucky, to be honest. And that I also basically instantly recognized what the problem was, because I've just seen it before. And the thing with the BIOS is just random. Like, normally there's just a single fault with the board, but if someone has been tinkering with the board, there sometimes are two faults, like in this case, where someone has probably tried to troubleshoot this, and in the process just destroyed the BIOS in it. And yeah, and again, we have higher power consumption in this case here for this board to start up. But there's nothing getting too hot or something similar like that. So let's get with the post screen, get into the BIOS. We can see high changing power consumption, high power consumption. Also on my tester right here. And that is a good indicator that we're going to have a new picture every second now. And we want to see this to go into Windows. Oh, I don't have my VGA plugged in. That is my problem. Let's give this board a reset. And then we want to check the USB and the Ethernet that is working. There it is. Now we're going to have the new picture. There's the BIOS splash screen. So now we should see the reticle of Windows spin up every second. There's it loading into Windows. That is very great to see. And we're loading into Windows. Let's see now for if the Ethernet is working. And the Ethernet is working, and I also have the recognition of the USB keyboard. I just now want to boot this up with another stick of RAM, just to be sure that the dual channel is working. And right there, going for it again. And let's see, there it is, 5 amps of power consumption. That's very good to see. And we are also booting with dual channel RAM. You can see that I put that in, but now there's 2 DIMMs in here. And I can also use the keyboard, and it is reacting to everything. So, yeah, just another board that I cannot tell you how that happens with the SIO. Like that partial active short, or like lower resistance. That is just, that I just had another board where I spent hours and hours trying to figure that out in order to find out how this happens. But yeah, RSM RST is a very important line for the CPU to see in order to create its sleep state 3 signal and in order to for the board to turn on. So if you have no reaction to the power button, that is one of the things that you will need to check in order to get a board powering up and starting up again. And yeah, the BIOS is just, it can always be another BIOS issue. Like, I'm not even methodical anymore about BIOS issues because I basically always flash the BIOS because it always can be a factor. There can be so many problems with BIOSes, and this case just happened to show it again that all of a sudden we had a completely non-working BIOS, just nothing in there in that chip. And yeah, all of the voltages were running 1.5 amps, 1.6 amps of power consumption is a very good indicator of the CPU not being initialized or the BIOS instruction not being initialized. So yeah, thank you very much for watching. I hope you enjoyed the video. I hope you learned something. And as always, all of my tools are linked in the video description. Thank you so much for watching. This was MainboardMedic. Thank you very much and goodbye.